Hello, my name is Dr. Jason Steffen. I'm a physics professor at UNLV. Today we'll be looking at data from NASA's Kepler mission to see if there is a way to turn those data into sound and gain some useful insight into the physics of these planetary systems. This attempt was inspired by a YouTube video by Tantacruel, where he bemoaned the fact that scientific data is often random and is therefore difficult to gain any insight unless someone takes care in how they convert the data into sound. The Kepler mission detected planets by watching the planets as they pass in front of the host star. If the planets pass in front of the host star, it will block part of the light from that star. The amount of light that is blocked is related to the size of the planet, and how frequently the light is blocked gives a measure of the orbital period of the planets in that system. Kepler's discovered some 4,000 planetary systems, and there are over 700 of them where multiple planets transit the host star. It's those systems that we're going to be looking at today. One of the advantages you have with planetary systems is there's important physics that happens in planetary systems that can drive the system into particular orbital configurations. When planets form in a gas disk, the forces in the disk can cause the planets to migrate with respect to each other, and if they migrate with respect to each other, they can capture into what are called mean motion resonances. These are system states where the orbital periods of the planets in those systems are ratios of integers. For example, 2:1, or 3:2, or 5:4, or 7:6, or something like that. This happened in our own solar system with Neptune and the non-planet Pluto. At some point in the past, Neptune migrated outwards and plowed into a ring of debris in the outer solar system called the Kuiper Belt. As it did so, it swept a number of small objects into mean motion resonance. And right now, Neptune orbits 3 times every time Pluto orbits twice. Ratios such as 2:1, 3:2, 4:3, 5:4, 6:5 also appear in music. If 2 strings are vibrating, and the ratio of the vibration is 2:1, that corresponds to an octave. If it's 3:2, it corresponds to a perfect fifth. If it's 4:3, a perfect fourth, 5:4, a major third, 6:5, a minor third, and so forth. So if you were to convert planetary systems to sounds, where the orbital period corresponds to a frequency, then when you have planet pairs that are near mean motion resonance, it will produce consonant chords, chords that sound good. On the other hand, if you have planet pairs that are not near mean motion resonance, then you'll get dissonant chords. This plot shows the orbital period ratios that are measured in the Kepler multi-planet systems. And these lines show the locations of these mean motion resonances where you would get consonant or good sounding chords. There are several planet pairs that are near these mean motion resonances. And those mean motion resonances correspond to this unique dynamical history where the planets have migrated with respect to each other. So if we convert the Kepler data into sounds and we hear these chords, then that will give us an indication of the history of that planetary system. There are other things that we can play with when we sonify the data. One of them is the volume of the chord that we play. Another one is the location of the home tone of the chord that we play, if it's higher in pitch or lower in pitch. The volume in this music is determined by the largest planet in the system. The larger the largest planet in the system, the louder the chord will be. The smaller the largest planet in the system, the softer the chord will be. For the home tone, that's determined by the orbital period of the largest planet in the system. The longer the orbital period of the largest planet, the lower the note will be, and the shorter the orbital period of the largest planet, the higher the chord will be. There's one last element that goes into producing the sound, and that is what order do you go through the systems. I could do this in discovery order, and that would make it a lot easier for the scientists to know what they're looking at because they can find the systems that they already know about. However, that doesn't necessarily match any physics because the planets were basically discovered in random order. Instead, I chose to rearrange the planetary systems in order of the innermost orbital period. So the planetary system that has the shortest innermost orbital period comes first, and the planetary system where the innermost planet has the longest orbital period comes last. As we go through each planetary system, I step through each combination of adjacent planet pairs. So for a 3-planet system, I'll play the chord that corresponds to the inner 2 planets, the outer 2 planets, and then all 3 planets together. In the video, the planets are spaced logarithmically, where equal distance corresponds to equal period ratios. The sizes of the planets that are displayed is the square root of the observed radius, and that corresponds to approximately the planet mass. That gives a basic overview of how I constructed the music of these Kepler planetary systems. For this music, the planetary systems are ordered from the more compact systems to the more spread out systems. The volume of the chords that are played corresponds to the size of the largest planet in the system. The chords that are played will run through all combinations of adjacent planet pairs in that system. In these systems, if you hear consonant, good-sounding chords, then that corresponds to planetary systems that likely migrated in their past and produced these mean motion resonances. On the other hand, if you hear systems where the chord is dissonant, then that implies that there was either no migration in the past or some disruption that happened that drove the planets away from mean motion resonance. You can also have situations where you can have a portion of the chord that is consonant with itself and a different portion of the chord that is consonant with itself, but those two halves of the chord are not necessarily consonant with each other. You can have more complex harmonies. And that could correspond to a situation where there was migration in two different regions in the forming planetary system, but those two different regions were not coupled together and did not evolve together. Anyways, my name is Jason Steffen. I'm a physics professor at the University of Nevada, Las Vegas, and I hope that you enjoy the music.